So this past week we learned about sample means and sample proportions and how representative they were of overall populations. But real quickly, let's define the differences between a population and a sample. A population is simply a social group somebody is trying to understand through research. And this could be based on any number of social criteria. For instance, somebody could be trying to learn about a particular ethnic group, for instance, African Americans or Latinos, or even looking at subgroups within those ethnic groups, say like African American women, how they differ from African American men or Caucasian men, and so on and so forth. Okay, but a population might be really, really large, and it would be difficult to survey every single person within that population. So in order to simplify things a little bit, researchers will take a sample of that population and survey them. Okay, and a sample is just a smaller representative portion of the population used to learn about that broader population. Now, a legitimate question somebody might have is how representative is that sample of the population? So for example, if you have a huge population of thousands or tens of thousands or even hundreds of thousands of people, can a sample of 100 really represent that broader population? And so what we're going to do is see how confidence intervals, we're going to learn how to create a confidence interval, understand what that means, and that'll help us understand how representative a sample is of a population. So once a researcher surveys a sample of people within a broader population, you can then get a mean or a proportion, and then you calculate what's called a confidence interval, which is a range of values surrounding that sample's observed mean or proportion. And it tells us how confident we are that the observed mean or proportion is for the broader population. Now there's a step you have to take in getting your confidence interval beforehand, which is calculating the standard error, okay, or SE. So you can do that differently for both an observed mean or an observed proportion. In order to get your standard error for a sample's mean, you just take your standard deviation and divide it by the square root of n. So it's not a real complicated formula. And this is described on page 231 in your textbook. Now, you know that getting the standard deviation can take a long time if you have a large sample size. So, if I give you a problem with a large sample size, then I will simply give you the standard deviation. And you just need to know that in order to calculate the standard error, you just take that standard deviation and divide it by the square root of n, or your sample size. Okay? The standard error for a sample's proportion looks a little bit more tricky, but it's not really that difficult. All you do is you take the sample's observed proportion, which is symbolized through the letter p. Then you multiply it by 1 minus p and divide it by your sample size of n. And then you take the square root of that entire equation, and that'll give you the standard error for a sample's proportion. Okay, that's described on page 242 in your textbook. And what we're going to do shortly is look at two concrete examples for calculating a confidence interval for both an observed proportion and an observed studies mean. Okay? But there's one more step. We have to take that standard error and put it into the formula for the confidence interval. So if you look on page 235 of your text, you'll see that there are three confidence levels scholars commonly use in order to see if a mean or proportion is representative of a sample: 90%, 95%, and 99%. I put all three up here because that's what's in your text, but really we're only going to worry about the 95 and 99% confidence intervals. Now what these mean are that if you go back to your Appendix B, we can see where a 95 or 99% confidence interval corresponds with different z-values. And again, you find a z-value in that first column, and you want to look then at the area beyond z, which represents the area usually on the tail of the bell curve, either on the right or left side. Now if you find the z-value of 1.96, you'll see the area beyond z is 0.0250. Okay, now what you want to do is, if we're saying there's a 95% confidence interval, then that means on each tail, both on the right and left side of the bell curve, we have a representation of 2.5%. Okay, you add those up and you get 5%. Likewise, if you look at the 99% confidence interval, then we have a corresponding z-value of 2.58 and an area beyond z of 0.0049, or 1/2 of 1%. Meaning if you add those two areas beyond z, or in the tail together, you get 1%. Okay? Now really what you have to know in terms of the formula is taking that z-value and putting it into the formula for your confidence interval, which is at the very bottom there in green. So you take either your observed mean or proportion for a sample, and then you do plus or minus the z-value of 1.96 for a 95% confidence interval, or 2.58 for a 99% confidence interval, and multiply that by your standard error. Alright, so let's take a look at a couple examples.